Hi everybody, this is the Algebra 2 lesson for section 1-4. So I need you to go ahead and grab your yellow state concept sheets that we have that has all the standards on the front. And we are going to talk about what 1-4 has and give ourselves that rating before the lesson. So 1-4 has I can solve equations. Now, generally, people come to Algebra 2 pretty doggone good at that, basic equations anyway. And then I can solve problems by writing equations. And notice, those are going to match our objectives perfectly. So again, you can skip the example and description. You could use that later to get ready for the test. But I need you to rate yourself before the lesson on I can solve equations, and I can solve problems by writing equations using that same 4-3-2-1-0 scale that we post in the classroom, where 4 is I can teach it to somebody, I got this. 3 is I know how to do it all, but I'm not sure I use the right words and stuff, so don't make me teach it to somebody. 2 is almost all of it. Might have some trouble with the harder ones. A 1 is I could do the basic ones, but then I'm going to be stuck. And a 0 is I didn't catch what you said there. I'm not sure how I'm supposed to do this and what these things are. Which, at this level, none of you will be zeros. You've all solved lots of equations already in exponential. So let's get started. Those objectives, we want to be able to solve equations, solve problems by writing equations. And the very first thing we see here is a statement that two expressions are equal. The root word of equation is equal. So we could do something as basic as 2x equals 14. We might have something like 3x minus 7 equals 65. Those are equations because we have two expressions on either side of the equals. And the equals means, hey, this is supposed to come out exactly the same on the left side of the equals and the right side. So this is the left side, and this is the right side. Same thing over here. Left side, right side. Because the equals is what separates the left and the right sides. So what we have to know is the properties of equality, and those are used to solve equations. And we know a lot of these, and like I said before, we need to know those names so that we can talk about how all of this works. But more importantly, Algebra 2 is really about, can you do it? Can you use these properties? Now, the first one we see up here is reflexive. Hopefully you remember that from geometry. Root word would be reflect, and that's because when you look in the mirror, you see yourself. That's the reflexive property. A equals A. Now, at this point, you might think, well, there's a really useless one. I don't think I've ever used that when I've been solving an equation. But as you get further and further in mathematics, let's say you've been working on a problem for a half a page, and you get to a spot where you realize, oh, if this is going to work, I'm going to need to introduce another variable. I need a new variable. This is what you do. A equals A, B equals B, X equals X, Y equals Y, and that introduces a new variable into what you're doing. The next one we have is symmetric. Root word would be symmetry. This means we can fold it in half and we'll get exactly the same on both sides of a sheet of paper. And that is, if A equals B, then B equals A. This one, every once in a while we do switch things around. We move the left side to the right side to the left side. And that's because it just makes more logical sense to us to do that. So the symmetric property is one that maybe, again, we've used it a lot. We just don't necessarily think about it when we're doing it. Transitive. Now, transitive, the root word would be, well, most people will look at it as trans, but you need to think of it as if it were transport, So if you're going to go to a job, so you would go from home to the light rail, and from the light rail down to the cities. Save some money on your commute. But really what you care about is you're going from home down to the cities. but you had to link that together with transportation and transport, and that's what transitive does. If A equals B and B equals C, then A equals C. So it says you really want to go from home down to the cities for your job. That's what you really want. But to get there, to save on your transportation costs, you use the light rail to link that together. So that's the transitive property. Substitution we use whenever we have to evaluate. Evaluate means take a number, put it in for the variables in the right spots, and then figure out what you get for an answer. So substitution says if A equals B, basically wherever you see an A, you could replace it with a B. Wherever you see a B, you could replace it with an A. Whatever's going to make it easier for you. Like I said, in Algebra 2, we're becoming master manipulators of numbers and letters. So all of these are going to help us as we work towards our objectives of figuring out, how do you solve these equations? How do you do that? Addition. Well, adding. That's what we're doing. So if A equals B, then A plus C equals B plus C. So what they're saying is, there's a rule in math that says as long as you add the same amount to both sides of an equation, it will be equivalent. So equivalent means in the end it would give you the same answer. And this is usually how we do it. We kind of line it up vertically and say, oh, that's going to be A plus C, and that'll be B plus C. But usually there's an X in there that we're solving for or something along those lines. So it looks a little strange, but it's something we do all the time when we have to add a number to both sides of an equation. So then I think logically, subtraction, oh yeah, that's when I subtract from both sides. So if A equals B, and we subtract a C, we have to do it from both sides, because remember, algebra, you have to keep that balance. What you do to one side, you have to do to the other. And that gives me A minus C equals B minus C, which is what we see right there on that red line of information. Multiplication. When we're solving, sometimes we have fractions that are connected to our x's, attached to our x's, because we're multiplying by them. And so sometimes we want to multiply by the reciprocal to get those out of there. So what we do is we look at it and say, okay, my equation is A equals B. I am going to multiply both sides by something. Let's just say we multiply both sides by 2. This is a little harder. I don't have good space here. But I could multiply both sides by 2. And it would say 2A equals 2B. And it wouldn't have to be a 2, because as this shows us, as long as we multiply both sides by the exact same number, we have that property of equality that helps us with our objective, solving equations. And then division. This is the same thing. If A equals B, then, well, now think division. So we're going to divide both sides by C, and usually it looks like this. We don't bother with the old style elementary division symbols in Algebra 2. That's just there to help you make the connections. But because we are dividing, and we know we can't divide by 0, we have to put this little piece on here. And again, that's called the domain. The domain are the inputs. What numbers could you put in? And in this case, because C is on the bottom of our fractions, it's in the denominator, and we have that one thing we can't do in math that just drives us crazy. You can't divide by 0. So there it is. We have to tell people, don't try and divide by 0. Put whatever else you want in there, don't divide by 0. So we're going to do some solving. Solving an equation, it's finding all the values of the variable that make the equation true. So we're going to use inverse operations. We have to think about how do we undo an equation. An example, if we see adding, we're going to subtract from both sides. So when you're solving an equation, what you need to do is follow the order of operations backwards, because we're undoing this. So when you do please excuse my dear Aunt Sally and you're solving, you start down at the bottom, which would be adding and subtracting. So what I do is I look for my variable, And I take a look at everything that's on that side of the equation because I really want that x alone. So here's my equals right here. And I realize, well, it's not alone because they're subtracting 8. How do I undo subtracting 8? I add 8 to both sides. And there's my answer. X equals -2. The got it. This one, I take a look at where my variable is. I see it's right there. I notice that's where my equals is. So I'm looking at the left side of this equation, and they have 12 times c, because when a number and a variable are right next to each other in algebra, that means multiplication. So what I have to do to solve this is divide both sides by 12. On the left-hand side, I will get c. And on the right-hand side, I have 18/12. But while I'm at it, I realize, well, 6 goes into both of those. So I'm going to go ahead and reduce this, dividing the numerator and the denominator by 6, and reduce that to 3/2, which, by the way, your calculator will do automatically for you. So here's my graphing calculator, and I want to reduce 18/12. Or maybe I just want to punch in 18 divided by 12 and take a look at what I get. And then I realize, oh, in Algebra 2, we're supposed to give fractions because fractions are more exact than decimals. In this case, I would take 1.5, but again, it is more accurate for a lot of the math that we're going to do for us to keep this as fractions. So, fractions are tough. Don't make me think about that. Okay, don't think about it. Let the calculator do it. Hit the math button and look at number 1. It says fraction. So I'm going to hit number 1 and enter. Well, look at that. Reduced it to 3/2 for me. Very nice, calculator. So again, a lot of things this calculator can do, and if you don't like working with fractions, this is the calculator for you. So we have our 3/2 there. And again, we probably should check our answers and make sure they're going to work. So if we go back into the one that I wrote in green, this would be -2 minus 8, which is, of course, -10. And over here, 12 times 3/2, you could punch that into your calculator, or you could do 12 over 1 times 3 over 2. Do a little cross-canceling. Yes, we get 18. So it's checked. At this level, I'm guessing you're probably feeling pretty confident in your solving equations. Doesn't hurt to check, though, especially on a test when you have lots of time to take care of things. Now I look at problem 2 and I say to myself, this is tougher. There's still parentheses in this. So I can't start my process of thinking backwards about please excuse my dear Aunt Sally because this isn't even simplified yet. To begin, I have to get rid of the parentheses. So I distribute the -2 and get -2y plus 2 equals -16 plus y. Now there's no more parentheses, but I have y's on both sides. I need those on one side. So what we recommend is that students choose the smaller of the two y's and move that one over. In this case, -2y is definitely smaller than 1y. So we'll add 2y to both sides and get 2 equals -16 plus 3y. Now that we have everything simplified and the y on one side, we can go back to thinking about the order of operations backwards. And since we have our y on the right-hand side, and the bottom step of please excuse my dear Aunt Sally is add and subtract, that's what we have to undo first. So I'm going to have to add 16 to both sides. And then divide both sides by 3. Checkable? Absolutely. You put the 6 in and you follow the order of operations and make sure it's going to work. So up here, if we put the 6 in, 6 minus 1 is 5. -2 times 5 would be -10. And if we put the 6 in here, -16 plus 6, -10. It works, so we've got it. So like I said, especially with the problems that have a little bit more going on, and it's a test, and tests count for 80% of your grade, if you have time, go back and check your answers. you can see, oh my gosh, I goofed up on this one. This doesn't work, you know, and that'll give you time to erase and try again. So this is the got it. I'd like you to pause the video and do this one yourself and see if you can get this to work out. Now that you've given this your own, well, good old college try, we want to go ahead and notice that we have parentheses in here still, so that's not simplified. So I have to distribute the 3 to both of the things that are in the parentheses, 6x minus 3. Then I get stopped again. There's another set of parentheses, so I have to distribute the negative 2. And now I notice I got more to do. I mean, on the right-hand side, there's 2x things going on, and so I need to put those together and figure out what's happening. And there's also 2 constants, which are the numbers, so they've got to go together. And something weird happens. 6x minus 6x is 0. Oh, that means there shouldn't be any x's on the left-hand side of this. Okay, that's cool. I can do that. And then negative 3 minus 8 is negative 11. Well, that just made this a much more basic problem. So now that I have this all simplified, I think add and subtract, undo that first. No, there's no addition or subtraction over there with that x. That's multiplication. To undo multiplication, we divide. Now here's what you need to know. You're not allowed to do this stuff in your noggin. You're not allowed to do this stuff in your head when you're taking a test. Each step is a point. Do not skip steps. Show every step as you're going through these. And again, double check it when you're done. Put it back in, make sure it works. If you want to use your calculator, remember, since this is a negative number, if you're going to put it back in, you have to use parentheses in your calculator. And there's already one set of parentheses to keep track of. So be careful that you're doing the double parentheses as you go through that. So that was a pretty doggone good start for our solving an equation objective, and hopefully you're feeling pretty solid about that. And we get to a word problem, and it says the map shows distances from towns in miles. So I see from Newton to Dayton it's 46, from Dayton to Highville 44, and from Highville to Essex 37. So it says the map shows the distances between towns in miles. You and your friend drive together from Newton to Essex, so all the way across. For some reason, I'm having trouble pronouncing Essex today. You drive first for a total of 40 miles. Then your friend drives 1.5 hours to reach Essex. What is your friend's average rate? Oh, well, up until that last sentence, they'd been talking about distance and using miles, and that was cool. And then all of a sudden, they're asking about rate. So I wonder, do I know something about distance and rate? And here they gave me a time. So to think about that average, or that average rate, we have to think, what do we know about distance, rate, and time? Oh, wait a second. In math and in science class, we have learned that distance equals rate times time. All right, so first thing I'm going to figure out is, what is the whole distance? So you either grab a calculator or you do it in your noggin and you take 46 plus 44 plus 37. Because that's how far they had to go. And when you add those all together, you get 127 miles. Now, to get that total, you are doing some driving, and your friend is doing some driving. So, this equation is about distance. We want to know, how are we going to get the 127 miles? The good news is, you know that you drove 40 miles. But for your friend, we don't know the distance. That's what we're trying to find. So we're going to have to use the fact that we know that distance equals rate times time to find that for us. Because we know the time. We know the time is 1.5 hours. What we don't know is the rate. So I'm going to use R as my friend's rate. Again, what we don't know is called an unknown, and we use a variable to hold the place for that. Oh, this is a two-step equation. So we would subtract 40 from both sides and divide by 1.5. And that would get us 58 miles per hour. Because again, you get the 58 and then you think 58 what? Oh yeah, they asked me for the friend's average rate. So that's how fast they're going. Miles per hour. And we have it. So again, it's a word problem, but it just uses a very small equation for us there of distance equals rate times time. Sometimes equations have a single answer. The ones we just solved, x equals, we got a number. Sometimes equations have no solution. There is no value that makes the equation true. Now we're going to know that because we're going to start solving and we're going to get to a point where we see something that says nonsense. 3 equals 7. No, it doesn't. It never does. So this would have no solution. So if you get a nonsensical answer, your x's are gone, and you get a statement that is completely false, you have no solutions. Sometimes we solve our equations and they actually work all the time. And those, there's actually a lot of names for those. This book uses identity. A lot of other books use all real numbers. And there's actually a math symbol for all real numbers. It's a capital R with an extra line down the left-hand side. So if you want to shorten up all real numbers to the math symbol for all real numbers, totally cool. I mean, after the Algebra 2 level, we really, should know some of the symbols that we use in math. So sometimes all values of the equation are true, and these are called, in this book, identities, and their solutions are all real numbers. So as you go through this, you're going to find out that there's a reason, and we're actually going to talk about the lines in Chapter 3. But for this one, if we are graphing in just x, just y, or in x and y, what we're doing is we're seeing two lines graphically. And sometimes lines don't intersect. There's a fancy name for that last year in geometry. Parallel. The lines are parallel. I'm going to put the runners on there so everybody can see. Parallel. Now sometimes all values make the equation true, and that happens because even though we didn't notice it, they were actually the same line. One line graphed right on top of the other, and that's why it's all real solutions, because where they intersect is where we find our answers. So problem 4 says, are we talking about a problem here that's always, sometimes, or never true? So always, we're going to see because we're going to get an answer 3 equals 3. That is always true. We might see 7 equals 7. Negative 15 equals negative 15. It's an always true statement. Sometimes is what feels normal to us. We just get an answer. I suppose I shouldn't use another 3 in there. We get an answer of like x equals 4. So we got one answer. That's a sometimes. Never true. 7 equals 82. That's never true. So we go through the steps that we would normally go through when we're solving, but strange stuff happens. If it doesn't, then it's a sometimes, because we are going to get one answer. So for A, I take a look at this and I notice, hey, there's too much gunk on the left and there's too much gunk on the right. It's because it's not simplified yet. I have to put my two constants, my two numbers together on the left-hand side. So 11 minus 7 is 4. Now I'm not moving them over. I'm just trying to pull them together on the left-hand side to simplify this a little bit. On the right-hand side, I notice that I have a 6x minus 3x. Well, I wouldn't leave it like that. I'd make it 3x plus 5. So again, we're not moving them over to the other side. It's not a matter of doing the exact same thing to both sides. We are just simplifying the left side and then simplifying the right side. So I get to this point and I remember, okay, what I'm supposed to do is put the x's together. I'll find the smallest one. Oh wait, they're both the same. So if I subtract 3x from both sides, I'm going to get 4 equals 5. No, it doesn't. That's never true. So I think, is it always, sometimes, or never true? This is the never right here. Our answer makes no sense. So this would be a never true. If they said solve instead of the directions that we have here, we would have to say this has no solutions. It doesn't ever work because when the x's are gone, it's a nonsensical statement. 4 does not equal 5. In fact, let me put the not equal to symbol right there. I look at B and I think, oh, this is very similar. I've got too much gunk on the left, so 6x minus 2x is 4x plus 5. Same thing on the right-hand side. There's a couple of numbers that can be put together here. Wait a second. 4x plus 5 equals 4x plus 5. Yeah, but let's say you didn't notice that. So you kept going. And you get 5 equals 5. That's always true. And that's what they wanted to know. If the problem says solve, you could say all real numbers. You could say infinitely many solutions. And again, this book says it's okay to call this the identity. It is. It's just that most books will focus on the number of solutions that you have here. Infinitely many solutions, all real numbers. Alrighty, we got a couple of got it's. So I'm going to ask you to pause the video, try this on your own, and then start the video back up again, see if we get the same thing. Can't start moving things over to each side because each side of the equals is not simplified. So we have to distribute the 3, distribute the 2, then we go ahead and combine things on the left-hand side and combine things on the right-hand side. This is not simplified yet. So again, it's just about simplifying each of those sides, not about starting to move things over. Now at this step, because we have 5x minus 12 and 5x minus 12, you might stop and already say, oh, this is always going to be true, because that's always the case. 5x minus 12 will always equal 5x minus 12. But again, let's pretend you were in the zone. You didn't notice that, and you get down to this. So this would be always true. Again, if they asked you, what are the solutions? You could say all real numbers, infinitely many solutions, or identity. All of those things would be okay. Now, B, not quite as much work, because there's no parentheses to take care of to simplify this first. But we still have to simplify the left side and simplify the right side. So 7x minus 4x is 3x plus 6. And on this side, we'll have 3x plus 4 because 12 minus 8 is 4. Then we'd say, oh, 3 is a smaller one. Uh-oh. 6 equals 4. No, it doesn't. That's an obviously false statement. And this will never be true. And again, if they ask you what are the solutions, then you'd say there aren't any solutions. No solutions. But we're trying to follow the directions here with the never true piece. So what we were doing today, Smartboard, wake up a little bit, was really working here. We had one example where we solved problems by writing equations. And no, we're not done with the section yet because we're going to need to cover literal equations, but we'll leave that. I think we've covered enough for today. And this is your assignment. So again, remember, the commas separate things. That means 11 through 25, you're just going to do the odds. 27 to 32, you're going to do all. And for 33 to 39, you're just back to the odds. I give you enough homework so that you see any type of situation that might show up on your test. And again, the homework is to transfer that knowledge from the short-term memory to the long-term memory. So make sure you follow up with the homework, how we're going to take attendance. Make sure that you are double-checking your work. Are your answers correct? If you got something wrong, check the FAQs, frequently asked question videos, and change them. Your assignments should be fixed. There should be no question marks put on there anywhere. If that happens, you're not going to get credit for the assignment until we figure out how to fix it. On a couple of the past assignments, people have left question marks, and I'm telling you in the comments section that you have to finish those and resubmit it. And for several people, it was an FAQ. There was a video made for that problem, and you just didn't bother to go through and take a peek at it. So please, in this time of distance learning, you have to use the resources. You have to know how to do all these problems. And I will see you in class, and we'll cover 1-4 day 2. Bye-bye.